It's Out of This World. Matthew Nicolantonio and Scott Sutherland with you again today. Being alone in the universe. It's a very popular concept that people like to think about and study. We know we're not alone. It's just a matter of how interesting. Or is there anyone like us out there? And one way that we are attempting to find out what is out there is through telescopes. Big, massive telescopes that are out in orbit. Started with Hubble, which recently passed 30 years of being out in orbit. But much more recently than that, back only not even 3 years ago yet.
That's right.
As of the time of this recording, the James Webb Space Telescope, which far more advanced than Hubble. So we'll begin with just a really basic background of what it is and how it differs from Hubble.
Right. So launched on Christmas Day 2021. It took about 2 to 3 weeks for it to reach its new home, which is at a point called Lagrange Point 2. It's located 1.5 million kilometers sort of behind Earth from the sun. This is this point in space where the collective gravity of the sun, the Earth, and moon all kind of tug on objects there to keep them following along with Earth, even though they're much, much farther out into space. And it orbits around that point to look outward and show us the wonders of the universe.
So let's talk about how it's a little bit unique in its shape.
Yeah.
When you think of a telescope, Hubble is just basically a giant version of what you might stick in your backyard.
Exactly.
But the James Webb Telescope takes on a much different shape.
Yeah, a little bit different. Basically, the mirrors that James Webb uses to gather the light for the targets that it views is so big that basically they couldn't launch it the same way that we did Hubble. I mean, Hubble was brought up into space by the Space Shuttle Discovery. So they stuck it in the bay, they flew up there, the astronauts picked it up with the Canadarm and put it out into space and let it go, basically. But there wasn't a rocket big enough to launch Webb the same way. They basically had to fold up this telescope into a much, much more compact form, put it in the clamshells at the top of a rocket and launch it up. Once it got into space, they were able to unfold it. It has an 18-panel hexagonal-shaped mirror, kind of like arranged like honeycomb with a space in the middle. And they had to unfold that, and they unfolded this immense sun shield underneath it. But it's otherwise open to space. Every
Which
other
seems risky.
Yeah, every other telescope we have up there is this enclosed tube with a mirror at one end. This one is basically the only thing that's protecting it is that sun shield from getting any direct rays from the sun that would heat it up and prevent it from doing its job.
And you were mentioning before we began recording off air that before it even was fully operational, it was hit. Which I'm sure was very concerning.
Yes.
What have we done?
they had it on the books before they launched that eventually this telescope is going to get hit by a micrometeorite or a micrometeoroid, and that's going to cause some damage. So they had that in mind. This one, it was in May of 2022, so not even 6 months really into the mission. Before, a full 2 months before they released the public science images. They detected that one of the 18 mirrors had a spot where some little pebble flying around in space came in and smacked right into it, which has been a fairly rare thing. I mean, it's been 2 years since then and nothing. So, but that was a bit of an eye-opener where it's still running.
Yeah. Now, we had also discussed that based on its sort of position in gravity, for lack of a better word term, it is relatively protected from bigger objects.
It would seem so, yeah. Like that Lagrange point 2 that it's sitting at is almost like a little hill in gravity, and it orbits around the summit of that hill. So if anything were to be coming along like a small rock or whatever, most likely it would be diverted around that
Around,
little
yeah.
hillock in the gravity.
Yeah.
This was just bad luck where it just happened to be in the wrong place because it doesn't stay in exactly the same spot all the time.
Right.
It sort of circles around
Mhm.
these points. So both the motion of that Lagrange point in Sun's orbit and its own orbit around that point kind of combine. That is it's a moving target,
Yeah.
right? So it's hard to do that,
So
but
the odds of being hit very
fairly low,
Yeah.
yeah.
Last point on this before we dive a little bit deeper into
Yeah.
what it does, its purpose, and how it's helping us.
Yeah.
We were sort of joking about, if it did sustain big damage,
Right.
repairing, getting to it, or being able to bring it back,
Yeah.
impossible.
Right.
To
It's
do it.
science
Explain
fiction.
why that is.
Science fiction. Basically, any spacecraft that we've built that could carry people either went to low Earth orbit or to the moon,
Mm-hmm.
like 384,000 kilometers away. Nothing we have that can carry humans has gone 1.5 million kilometers away. And we don't have anything right now that can do that. Orion being built right now is rated for the moon.
Mm-hmm.
Theoretically, maybe you could get it to fly farther out and to get to that, but the concept is just baffling as far as like we don't have what the necessary infrastructure to do that. We don't have a rocket that can get people out there. We don't have a spacecraft that could carry them properly. We just don't have the capability. So it's just cross fingers.
Yeah.
It's not a great way to go through life, but yeah, the odds are low that it'll break. But if it does, that might be it.
All right. So it's totally science fiction to be able to repair it. So
Yeah.
coming to theater summer 2026, a story about the James Webb Telescope.
Yeah, there you go.
Mission to repair it.
Perfect.
All right. All jokes aside, let's dive into what is the purpose of the James Webb Telescope in a grand scale.
Right. Mostly, it's an infrared telescope, which is a little bit foreign to the way we think of telescopes. You have one in your backyard. You're looking at things that you can see with your eyes. Hubble mostly did that as well. It sort of peaked into the ultraviolet, beyond the violet and blue, to detect the higher energy stuff, and it peaked a little bit into the infrared, past the red into the lower energy stuff, just to give us a little idea of what we were seeing beyond that, beyond the visible, that is. James Webb is completely infrared. So it's looking at the stuff that is completely invisible to our eyes. In one way, that's the best thing to do for this particular telescope for two reasons. The first is that all the dust, all the nebula and galactic dust and even intergalactic dust out there blocks most wavelengths of light that pass through it. Even radio waves suffer from this, which are the longest type of electromagnetic waves. But all the high energy stuff will get blocked by it. Visible light gets blocked by it. Infrared doesn't. It's at just the right wavelength that it just slips right through all of these, clouds of gas and dust that would otherwise obscure our view. So when you're looking really far out into the universe, having the clearest view is best, and that's what James Webb gives us. Also, it's allowing us, by being purely infrared and looking deep into the infrared, it's giving us the farthest look out into the universe that we possibly can get right now. And that's due to the expansion of the universe, basically, is that as the universe expands, the space in between objects gets bigger, gets larger. Any light passing through that expanding space also gets expanded, gets stretched, because light travels like a wave, and, so it's like a little rises and dips and rises and dips, and the wavelength of between one crest of the wave and the next crest of the wave determines what kind of light it is, whether it's blue or gamma ray or infrared. And so as you go farther out, as you look farther out into space, that stretching gets bigger and bigger and bigger and bigger and bigger. So the light gets pushed sort of farther and farther and farther into the red and the infrared until, basically objects at the farthest distance that we can see, that we can gather light from, are everything, all the visible light that was being produced by a galaxy out there. So if we were much, much closer to it, we could see it with our eyes. From here, 30 billion light years away, all of that light has been stretched into the infrared. But that's what Webb looks at. So
what exactly has it seen that's sort of so interesting that we have not been able to see this way before?
In some cases, they've just been, in most cases right now, they've been just sort of like, we've looked at the Carina Nebula before with other telescopes in Hubble. Let's look at it with James Webb to see what it shows us, because it'll reveal more details about it. Let's look at Jupiter the same way, Mars, Pluto, whatever, in our own solar system. But also, it's been looking at things where we didn't have the capability of seeing, like, say, supernova 1987A happened in the Large Magellanic Cloud. We saw the light. Other telescopes have seen the expanding ring of gases that's, puffing up away from that explosion. But we were never able to figure out what's at the core of it. A supernova usually generates either a black hole or a neutron star. But they couldn't find any direct evidence of which it was. Webb was so powerful that it saw the direct evidence that it's probably a neutron star. So that's a discovery. Like, we didn't know that before, and Webb showed it to us. But there are 3 planets that are potentially habitable. Like, they're warm enough, roughly, that they could have liquid water on their surface, but do they have the right conditions for that?
So theoretically, the James Webb Space Telescope can look back over 13 billion years.
Yeah.
That just... you hear that and it's just kind of mind-boggling.
Yeah. I mean, Hubble has seen back pretty far.
Yeah.
But it needed help. Like, it needed assistance from the universe itself kind of help, where some gravitational lens caused by an immense galactic cluster happened to bend space just right, that some far distant galaxy that behind it that we'd never be able to see otherwise happened to have its light, magnified by that lens, and so we could see it. Webb just goes, I'll just take a look.
I'll just take a picture.
I'll just take a look. A couple hours, give me a couple hours. It's fine. So it's seen back. It's a very complicated name that they've given this galaxy, but it's the earliest they've ever seen. I believe it's in the same cluster of space, or same little postage stamp size area of space that Hubble took its ultra deep field in years ago. But it's from roughly 300 to 400 million years after the Big Bang. So 13.3 or 13.4 billion years ago. And now the distance is like 30 something billion years because of the expansion of space. Yeah. But yeah, that is the infancy of the universe.
So are we able to sort of measure exactly how much better James Webb is than Hubble?
There are probably a lot of metrics for that. Basically, it's bigger, and they read different things, so it's not always a fair comparison. But
newer is always better.
But newer is always better. But based on the fact that, like, take a look at the infrared images that Hubble produces and the infrared images that James Webb, with a mirror a little over 2.5 times, I think, size.
Okay.
So they're so much better resolution, much better instruments to read the data for the cameras that capture the light. So it's the resolutions are marvelous compared to what Hubble did. Hubble wowed us with its views. James Webb blows our minds.
And the pictures that we see from James Webb are just like difficult to put into words. Just how cool,
mind-boggling. Like just the tiniest details that you can see just by zooming in.
Yeah.
And not only that, but everything that it looks at, almost everything that it looks at, in the background, you see thousands of galaxies. And this is just like little tiny areas of space where you could take a photograph of the whole sky and it would fit in a little postage stamp size area. and it shows a big nebula or whatever, but behind that, or even looking at Jupiter, behind Jupiter, hundreds of galaxies in that tiny little space in the background, just showing us how immense our universe really is.
Yeah, absolutely.
Yeah.
So let's talk a little bit more about what it has discovered. Specifically, we're going to talk now about exoplanets.
Yeah.
So let's first briefly, what exactly is an exoplanet?
So an exoplanet is a planet that is orbiting a star other than our own.
Okay.
So any star out there other than our sun that has a planet, that's an exoplanet.
Okay. Easy enough to remember. So how many, or I guess Webb hasn't really discovered new exoplanets, but it's sort of given us more detail about them.
It's capable of discovering exoplanets, but it seems like that would be something more of a, we have an idea that there might be an exoplanet around this star we want to see, or it accidentally does because it's looking at a star for a different reason. But mostly, it's used for follow-up observations. Because the way it can work is it has the technology to block the direct light from the sun so that it can gather the data just from the planet, but it can also watch as these planets transit their star. So it can say, okay, we'll watch. They just did that recently where it took roughly a day's worth of data, but this planet that it was looking at, I believe it's WASP 43b, as it's called, is this giant Jupiter-like planet that orbits really close to its star. It takes 19 hours to orbit around its star.
So which a year is 19 hours.
Its year is 19 hours. The telescope looked at the pair of them and got light from both, and then the planet went around and dipped behind the star, and so it got just the light from the star, and then the planet came out again, and then it got the planet passing in front of the star, and so it got the combination of that. Using that, the scientists were able to then subtract away the light from the star and have just the light from the planet, and then split that into its colors, like you would do with a prism, and looked at what gases were in the planet's atmosphere, and found that it was mostly clear, like I guess you would say sunny skies on the starward side, very cloudy on the other side. And they were able to map out, based on what they technically didn't see in the atmosphere of that planet, that the winds were howling around that planet at 8,000 kilometers per hour.
Wow. That's a windy day.
That's a very windy day.
As of April 2024, we have sort of discovered or observed more than 5,000 exoplanets. Is that correct?
That's the confirmed numbers, like 5,600 confirmed worlds. And there's probably at least that, if not more, that have been unconfirmed so far, that we just have the inkling that they're there.
So what do we know about these 5,600 exoplanets?
That we know that a lot of them are rocky, not specifically like Earth, but close. We know when they're in their habitable zone. We can read what their star is and how much light and how much energy their star produces, and then say there's a range where that planet would be warm enough to have liquid water on its surface like Earth does. But it also could be a little bit like Mars, could be a little bit more like Venus, where it's had some sort of runaway greenhouse effect. So that they don't know yet. That's where Webb will come in. We'll be able to read these planets the same way it did with that giant Jupiter-like one, and tell more about the composition of their atmosphere. If they have an atmosphere, they've already done that a little bit with. There's this really, really exceptional nearby planetary system called TRAPPIST-1.
Okay.
It's called that because that's the telescope, the survey that discovered it. But it's 7 rocky planets orbiting really, really close to this small red dwarf star. Like it's this little tiny compact solar system almost that could fit well within our own orbit of Mercury. Very, very small. So it takes only hours for these planets to go around the star. After they were being detected, other telescopes have looked, and they're trying to determine, do these planets have an atmosphere? Is this really, really active little red dwarf star stripping these planets of their atmosphere, like our sun did with Mars once it cooled and lost its magnetic field. But there are 3 planets that are potentially habitable. Like, they're warm enough, roughly, that they could have liquid water on their surface, but do they have the right conditions for that? So basically they've been using Webb to go systematically planet by planet out, and they've done the first 2, the closest 2 to the star. Then I guess they'll continue on with the 3rd one, the 4th one, the 5th one, the 6th one, and so forth. But it's those middle 3 that they're really, really interested in, because those may be the ones that we detect traces of water, traces of an atmosphere. And then they'll look for other things, like molecules that only are known to life, right? Only life creates these molecules, whether it's from algae or corals or something that might be a bit more technological. Like, what if we found a planet out there that had degraded ozone because of chlorofluorocarbons? That would hint very strongly that there's an intelligent, technologically advanced species on that planet, right?
So back to what we talked about at the beginning, of trying to discover if there's anything out there that's like us.
That's right.
So, we talked about 30 years between Hubble and James Webb.
Yeah.
But it doesn't seem like there's going to be 30 years before we get sort of the next sort of advancement in these types of telescopes. We know that both NASA and European agencies are working on sort of the next phases. Can you talk a little bit about that?
So last year, or in 2023, the European Space Agency launched Euclid, which is a dark energy and dark matter telescope. In 3 years from now, NASA is...
So 2027.
2027, NASA is planning on launching the Roman telescope, the Nancy Grace Roman telescope, which will sort of complement Euclid. We'll also look into dark energy and try to suss out what exactly or why, what is making the universe expand so quickly, right? And faster all the time. But it also will have similar capabilities to Hubble in being part visible, part infrared telescope. It will look for exoplanets and so forth. And then beyond that, they have another telescope that's still on the drawing board, still only on paper, but it's the Habitable Worlds Observatory. And the idea behind this is to put a Hubble-like or Roman-like telescope up there that has a sun shield that sits out in front of it. And then the telescope will look just beyond it. It will use that sun shield to block the star's light so that it can see planets orbiting around the star.
Right.
And get the first or maybe the best direct images of planets, and look for those ones that are really, really close into the star rather than these giant gas giant planets that we've imaged so far, to find those ones that are in the habitable zone of their star and take images of those to, again, read their atmospheres and find those potentially habitable worlds out there. Because with a universe this big, the Earth cannot be the only habitable place out there.
You would think that how in all of this vastness are we the only place where life can develop in this way.
To borrow from Carl Sagan, it's an awfully big waste of space.
Yeah.
Right. If there isn't any life out there.
That's a good way to put it. All right. Yeah. So we may not be alone in the universe in the way that we might think, but you are not alone when you watch Out of This World, because we get a lot of great info from Scott Sutherland. Scott, thank you once again for being with us and enlightening us on all things telescopes and exoplanets and beyond.
Yeah, this has been really fun.
All right, this has been Out of This World. Thanks for watching.
It's very pretty out here.